We look up and see a blinding, dominant force. For all of human history, our sun has been the absolute ceiling of scale, a colossal fusion reactor dictating the rhythm of life on Earth. But out in the wider galaxy, our star barely registers. If you zoom out far enough, this massive anchor of our solar system shrinks down to the equivalent of a microscopic speck of dust. When astronomers pointed their infrared cameras toward the Scutum constellation, peering 20,000 light-years across the Milky Way, they found objects that shatter our baseline for normal. We live our entire lives orbiting a quiet, tiny star, completely insulated from the physical realities of the galaxy's true giants. One of those giants is Stephenson 2-18. It is a red supergiant, burning at a remarkably cool 3,200 degrees Kelvin, giving it a rare M6 spectral classification. This animated diagram illustrates the math required to measure it against our sun. You could fit 10 billion of our suns inside the physical volume of Stephenson 2-18. Humans simply do not have the evolutionary hardware to visualize 10 billion of anything, let alone 10 billion stars packed into a single cohesive sphere. To actually grasp the dimensions of this hypergiant, we have to pull it out of the Scutum constellation, drag it 20,000 light-years, and drop it directly into the center of our solar system. The moment Stephenson 2-18 takes the sun's place, a wall of dark red plasma instantly expands outward, incinerating the inner solar system. Mercury and Venus are gone in a fraction of a second. As the star's edge crosses our orbital line, Earth is entirely engulfed, instantly vaporizing the oceans and the crust. The plasma boundary doesn't even slow down. It pushes further out, consuming the barren surface of Mars. Next is Jupiter. The immense gravity and thick atmospheric bands of our largest gas giant offer zero resistance as it vanishes inside the star. The expansion finally stops right at the orbital path of Saturn. The physical body of a single star has completely erased half of our planetary system just by taking up space. But the physical size is only one metric. Stephenson 2-18's energy output is millions of times brighter than our original sun, flooding the outer reaches of the system with intense radiation. This schematic shows where the new habitable zone, the region where liquid water could theoretically exist, would end up. It gets pushed deep into space, 10,000 astronomical units away from the center. Yet this distant zone is completely hostile. The star would constantly bombard that ring with lethal wave pulses of ultraviolet and X-ray radiation. If a planet were somehow placed in that distant orbit, the mechanics would be agonizingly slow. Traveling that immense circumference means a single planetary year would take 150,000 Earth years to complete. Surviving the initial physical expansion wouldn't matter. The extreme physics of this hypergiant stretch the mechanics of time and the requirements for life into completely unrecognizable, dead extremes. There is a strict cosmic penalty for growing this large. Red supergiants achieve their massive scale by burning through their fuel at a rapid, highly unstable pace, resulting in very short lifespans. In just a few million years, the internal pressure will fail. Stephenson 2-18 will experience a catastrophic core collapse, erupting into a blinding flash of kinetic energy known as a supernova. When the raw energy of that explosion finally clears out, the luminous giant will be gone. In its place, a dense, gravity-crushing black hole will remain. The largest and brightest objects in the galaxy are bound by their own physics to eventually collapse into its darkest, most destructive voids. This violent, system-erasing life cycle is the exact opposite of our reality. By comparison, our sun is remarkably quiet, stable, and completely boring. But a boring star is the strict physical prerequisite for evolution. It provides the billions of years of predictable warmth required for complex life to develop, without being vaporized or irradiated. Our small, unremarkable position in the galaxy isn't a weakness. In a universe dominated by volatile, short-lived monsters, orbiting a tiny, predictable star is the ultimate cosmic lottery win.